Hello. Hello. Yeah, hello. So today I would like to present my paper. It's called uh, today I would like to present my paper. It's called a full gradient represent. Hello, yeah. Today I would like to present my paper. It's called full gradient representation for neural network visualization. So today I would like to present It's called full gradient representation for neural network visualization. And yeah, so this is as part of a seminar in explainable machine learning. So yeah, see maps, which are both sensitive to the inputs as well as sensitive to the network that we are visualizing. So they try to be sensitive to both the inputs and the networks we are visualizing. And yeah, this paper builds on like previous papers that have been generated here. This paper presented here with saliency maps, namely the integrated gradients for the ICM paper and yeah, other papers here. So, okay, let's start with the motivation. So the motivation for this is basically we have basically we want to make our models we want to make our models interpretable. So classically, neural networks which are used for classification and regression tasks are mostly black boxes. And as we've seen here before, what we want to do is we want to make it possible for us to have some confidence in their judgments, and we want to do this by what is it? Yeah, by making like we want humans to be able to oversee where the decisions coming from. That means we want human beings to know what the causes for these decisions are. So for example, in this case, we want to know we want to be able to ask questions which are both of a global nature and a local nature. So when we say we want to ask questions which are of a global nature, what we mean is that we want to ask, given an input, which are the features which are important for this particular input. And for questions of a global nature, sometimes we're not sure that we are capturing all the relationships in our networks. So we want to ask like global questions like, is like are all the neural network outputs accounted for? Is there a systemic bias or something like that? And are our saliency maps capturing everything about the network's decision making? And that is the distinction that we're going to draw. So saliency maps basically is an attribution technique which is commonly used in image processing, where we take an original input, we get the machine's decision for this input, and then we based on this we decide on which are the pixels in the input which are salient for the decision that we're making. So for example, if you're recognizing an animal, for example, a bird, then we want to find out the pixels which are most responsible for us recognizing like this bird. So you can see over here, for example, the red pixels are, so we go from a red to blue scale, and the red pixels are the pixels which are most salient, followed by the green pixels which are the blue pixels which are the least salient. So we go from R to B in terms of saliency. So several of these techniques have already been introduced, and so we try to introduce here is the full gradient representation. So basically, the problem of saliency maps we have got an intuitive notion of what saliency is. So if, for example, if you ask a human being, if you want to decide there's a bird in this picture, if you want to outline it, a human being can say that, okay, what is important is these pixels surrounding the bird are salient for my decision making. But if, for example, the background pixels would be less salient. But as humans, we only have an intuitive notion of what it means to be salient. We don't know exactly. We don't have a way to. We don't have a good way to formalize this notion. And what we would like to do is we would like to learn a function which takes as input like this input and our network and its decision, and basically able to say that for this network, what is salient in its decision are these pixels. For this input, this network, what's salient in making a decision will be these pixels. So because there's no intuitive notion of what defines a saliency map, so what we have to do is there are several approaches to this. So previously it was a purely intuitive notion, and then later papers like the ICM paper is to ask the question of how can we define axioms which make saliency maps relevant. So and what would be properties of saliency maps that we want to capture. So for example, so in this paper we basically define two axioms which we think will be important for defining saliency maps, and these axioms supersede some of the axioms that have been presented later on. So these are the names are a little bit unintuitive, but they are weak input dependence, and we'll see later that that corresponds to local importance, and completeness, and we'll see later that that corresponds to a question of global importance. So what does it mean when we say we want the network uh, to display the property of weak input dependence? What we mean to say is that uh, if the network's output, so the network is, we're going to say that the network is, for example, in this case, supposing our neural network is a ReLU activation function, so it can be modeled as a piecewise linear model. So what we want to say is that given that we have a piecewise linear model, any saliency map that we're going to generate for this, it's going to be such that if we restrict our inputs to a particular region where where we are on one of these planes, then in these regions our saliency map is going to be fully representable using the parameters of this plane. So that means that our saliency map is going to be fully representable using WIBI. So for ReLU networks, they can be seen as piecewise linear models. So yeah, so in that case, we are going to say that, okay, we're going to be weakly dependent on our inputs. So all we are going to require from our inputs is that they lie in a certain region, where the function behaves like a plane, and for this, and our saliency map is only going to be determined by these things. So we can see that this captures a certain notion of local importance, and the way we can see that is that because all the inputs are because we are going to be deciding, because the neural network outputs are going to be decided purely using the weights and biases of the particular this thing. What is it called? Weights and biases of this. So we're going to say that we're going to capture like this sensitivity of the model towards input changes. So basically, we're saying that if the model is not going to if the model is, because our function, the saliency function, is a deterministic function, we're going to say that because our model is whatever, like our model is going to return a classification uh, which is which is what is it called? For any perturbations of xi, that means in our region of planar region, for any perturbations of this, our saliency map is going to basically say that these perturbations are not relevant if we are staying within this particular input region. So this is going to capture the notion of local importance. So one example in one of the papers that we are reading is, for example, when we are doing when we perform a mean shift on the input, we see that our gradients are invariant to this shift, and we want to capture this notion that since the model is going to model classification is not going to be affected by this mean shift that we're going to do on the inputs, we do not want our saliency map to also shift based on this input. So we are getting this kind of input invariance by requiring this weak dependence. So by saying that, okay, we're going to define this region in which the saliency maps are not going to change. And yeah, so you can see already from this thing that the gradient represents is so in our previous cases where we did input gradients, we would basically say that, okay, our input is changing, but our gradient is not changing. So in these planar regions, you can see that the gradients are constant. So we would expect that the gradients would be constant here as well, and which is what we find with several gradient methods. Okay, so the other property we're going to need, we're going to ask for is that a network should be a network should fully capture all the inputs, should fully capture the behavior. Our saliency map should fully capture the behavior of the model. That means that if we are given just the saliency map and the input that we have gotten, we should be able to predict the model behaviors for all networks and all inputs. So the saliency map and the input is the only thing that we need to be able to recreate the model inputs. So which basically we're saying we have covered, it's like kind of coverage for our model. It's kind of, you can think of like we are covering all the cases of our model if we satisfy this completeness requirement. And completeness with baseline is basically says that what we want to do is we want to capture the fact that is basically a generalization of the completeness thing, where in addition to, and this is an example we have seen before. So in addition to the model output, we are going to say that, okay, we are also going to give you a reference baseline and a saliency map of the reference baseline. And with this baseline, we should be able to recreate the difference, the model output difference between what we expect it to be and what it is. So yeah, so basically completeness is basically we're saying we are capturing the full model output distribution. So yeah, so okay, so now one of the things, so when we create these two requirements, that is weak input dependence and completeness, when we posit these two requirements in this paper, what we find is that for piecewise linear models, in fact, that these two requirements are not satisfiable, and we can see this by noting the fact that our saliency map is d-dimensional. So, supposing we are in one of these piecewise linear regions like UI, which I show over here, we see that. So we see that in order to be fully determined, we need to posit like two parameters, the weights and the biases of this network. Now for this piecewise function, which you have seen before, we see that we would, supposing we are posited like we need n such weights and biases. So depending on the number of regions we have. So if we have these n such regions, then when we posit that we have inside one of these regions, then the weights will be d-dimensional, and the bias will be one-dimensional. So the number of parameters you need to describe this neural network will be the behavior of the network in this region will be r d plus 1. And so basically what we have is, and yeah, similarly, like if you want to distinguish between f and f prime, which are two networks, which supposing they behave the same in every way, except for they behave in this region, they behave differently. In order to be able to distinguish which of these networks we are currently dealing with for our completeness axiom, we would have to, so you can see, for example, like we can posit, because of our weak input dependence, we are going to map to a particular saliency map in the d dimensions of which is the same dimensions as the input. So when we map to this from this d plus 1 dimensions to d dimensions, we basically are going to end up creating uh, many to one map. So when we go to reconstruct using our for our completeness axiom, when we go to reconstruct from a saliency map and our input, which of these weights resulted in our output, which of these weights, which of these outputs we should consider f or f prime. We will not be able to distinguish these two unless these two are basically the same. Because of this one to many map, this is basically indistinguishable. So in order to make a distinction, what we have to do is, so basically when we go from when we want to satisfy these two criteria of weak input dependence and completeness, which are desirable criteria for our network, we run into we run into the fact that these two are not commensurate, and therefore they are incompatible, and therefore we cannot reconstruct the network, and therefore we cannot have a completeness, and we cannot satisfy completeness and weak input dependence together. So, so the paper that we have basically says that this is a problem because we are not capturing the behavior of the when we capturing just the gradients of the inputs, we are not capturing the behavior of the function as the biases are changing. Biases are changing, and we are not capturing the behavior of the function with respect to any particular input point, the behavior of the biases with respect to the input points. So in order to capture this, what we need to do is we need to consider this additional term called bias gradients, which is basically the gradient of the network with respect to the bias terms. So if we have like many layers in our network, we'll have biases on each layer. So this bias vector is like a concatenation of all these biases, and the paper shows that we need to use both the input gradients as well as gradients with respect to these biases to fully capture the behavior of the function, to fully be able to capture the behavior of the function. This full gradient representation, and this is completely required, and this full gradient representation is d plus f dimensional. So for all the biases, we have to capture both the input dimensions. It will be r plus d dimensional. So currently, if you look at our saliency maps, they are all d-dimensional saliency maps, and therefore they are not able to capture this notion. So yeah, so we add this additional term, but this obviously increases our explanation by a lot. But what we get for this is we get a guarantee of completeness. And interestingly, what we also see is that in the input gradients in these linear regions will have a constant gradient. So but we also see what happens is that in these regions the bias gradients also have what is it called, a constant are constant. So this representation is actually capturing this notion of a weak input dependence. So the G so this our complete representation in these linear regions where model behavior where the model behavior is fully being captured is also displaying a constant is also is the G the our explanation is constant for these regions where the input behavior is the same. So what we want to do is we want to generate the saliency maps for a particular network. So the most common network of these is the convolution network. So here is an example of VG16 which uses like a bunch of 3 by 3 kernels. Uh, so uh, so actually what we find, and these are hierarchically stacked. So as we go down in this network, we increase the receptive field of this network. So and uses a ReLU activation function. So what we see is that the spatial structure of the convolution network allows us to basically visualize both the input gradients as well as the bias gradients, and we can do this using an aggregation function. And the way this works is that and the reason why this works is that because our bias gradients are of in this particular case we have a kernel which can be of size 2k plus 1, where for example here in this case we have a 3 by 3 kernel, so k is 1 here. So supposing we have a weights kernel of 2k plus 1, so this is going to be convolved with this full input. And let's assume, for example, that we do not cause downsampling because of this convolution. What we are going to also have is like a bias term. For each one of these filters, we're going to have a bias term. And because these bias terms are shared for this filter, this bias term is going to be basically the same for every pixel value. So basically our biases that we are going to learn, biases that we have are going to be d-dimensional biases. So for each input pixel, there'll be a bias term. So what we want to do, so what that means is that when we visualize this, we visualize like we can visualize not only our input gradients, but also this per channel bias gradient. So which is going to basically represent what is the effect of this new, what is the effect of a change in bias and input for this input, what is the effect of a change in bias for this particular neuron. So we're going to basically capture the sensitivity of this neuron for the network's decision on this input. And as we go down the receptive field, we're going to increase as we go down the network, we're going to increase the receptive field of this thing. So even though we cause a downsampling to happen, we're going to increase the receptive field. So here in this case, when we're not downsampling, we can combine the effect of these bias gradients by basically adding over all the channels of this particular layer. And yeah, so there might be some issues with science. We're going to do some post processing on this. So one thing that we have to do in order to match, one thing that we do in order to, so the author suggests like one post processing function in order to create the saliency maps is to use like a bilinear upsampling and rescaling. So basically, in order to make standardize on the size as we are going to be downsampling, we're going to just basically rescale, take an absolute value so that the sign is not significant. and we are going to basically cause this network to we are going to basically then do this layer. We're going to aggregate all the channels in a particular layer, and then because the post processing is going to be in retain our dimensions, we're going to aggregate over all these layers, and that's how we're going to compute the bias gradients. And when we combine this with the input gradients, we are going to get aggregation, which not only takes takes the input gradients into effect, but into account, but also takes into account the saliency of a region for a particular neuron across the layers. So we're going to compute bias gradients for all our convolutional layers, and then we're going to finally aggregate them by just basically summing over them. We do a post processing and summing over them, and we get a saliency map in RD. So the important point that the author makes is that this saliency map is again not going to satisfy both input dependence and completeness. So we still need to take into account the effects of both we still need to take into account the fact that we are still limited to a d-dimensional map when we're doing a saliency map. So the authors suggest that this particular representation is useful for detecting saliency maps for certain metrics, and they optimize for certain metrics. But there are other metrics. For example, they have a digit reconstruction where this would no longer be because we have this impossibility result. We cannot satisfy both weak input dependence and completeness. So we run into an issue where even now, because our true representation is still going to be our gradient representation, which is R plus D dimensional, but for the purposes of our input, we still need to have like our d-dimensional map will still suffer from the incompatibility of weak input dependence and completeness not being able to hold together. So this is going to this is basically dependent on the kind of post processing we use. The author argues that empirically this is like a good post processing algorithm. Based on some metrics that he presents. So the results, the two metrics that we present, that the author says that that justify this post processing step is, for example, the pixel perturbation test. So that means if we replace k image pixels corresponding to the least salient pixels. So instead of replacing the most salient pixels, the author we replace the least salient pixel. And the author argues that the reason for this is that we want to create less artifacts in the input, and we're going to just see that what is the change in the output. So if our model is identifying the least salient pixels correctly, then we are saying that the model output should not be changing towards this pixel perturbation. So as we remove a greater number of pixels, because we're not removing salient pixels, our network is going to still be able to make its decisions accurately. So deleting these pixels should not be changing network output. So this is one quantitative way for us to look at pixel perturbations to determine whether or not the model output is changing. So here we argue that lower is better. So we see that we can, as we remove the output fraction, the fraction of output which flip or change their decision is very small compared to is lowest for the full gradient post processing that we apply to our full gradient representation. Another quantitative results we use is remove and retrain. I think this was presented here. So here we remove the top k pixels, but instead of just looking at the change in network output, what we say is that if we retrain the classifier, because we're going to when we remove the top k pixels, we may be introducing artifacts. When we retrain the classifier based on these top k pixel removals, the classifier should have a lower accuracy depending on the number of pixels removed. So if we remove, so we can see that the top k pixels got removed, and we still we lost the most accuracy for the top k pixels for just 20% of the pixels removed. Full-Grad accuracy dropped the most. So we argue that this is evidence for our post-processing to be identifying these top k pixels being removed. So because it is a qualitative step, better, but they are also more localized to regions of the image. For example, here the author is saying that because the head is a key in determining the network output, this is so we are localizing our saliency better using this methodology. So in conclusion, yeah, so the author, so the strengths of this paper, which I felt were the author did a fairly good job of introducing concrete criteria, like concrete axiomatic criteria for what are difficult notions. So I didn't show this here, but there are unintuitive breakages that happen when the model is not satisfying these two axioms, so there are some unintuitive results that can happen. So this is kind of pointing to the way that you actually do need the complete information of Full-Grad in order to make a decision for your network output. And in the absence of this, we cannot guarantee these two, completeness and weak input dependence, are holding. And because these are not holding, so because these do not hold, when they do not hold, then basically we need to be careful about the conclusion that we can draw from our saliency maps. So certain pixel regions will be, if only weak input dependence holds, in certain unexpected pixel perturbations will cause the model to not change its output, for example. Okay, so here we showed, so here the results were mostly based on ReLU based activations. So the author makes a point to also show the fact that we could have used some other activation function, but this other activation